Hey everyone, today we are going to discuss a wireless system uh, problem. We have a SIMO system, that is single input and multiple output, and we have the system design equation as a y bar, which is a vector of r cross 1, which h bar x plus n bar. So these y, h and n are the vectors because we have a r receive antenna and single transmit antenna. X is the parameter which has been transmitted from the transmitter. Now n is modeled like it's a Gaussian noise where elements of n, which is ni's, will be correlated with the given correlation matrix as a Rn, let us assume. Now we have to design a combiner at the receiver which can be used for the decoding purpose. Let's begin. As we know that this noise is Gaussian and uncorrelated, assume its covariance matrix as R. First, do noise whitening at receiver. As we know that for noise whitening, what we need to do? We need to multiply this received vector y with the Rn inverse 1 by 2. Assuming this new vector as a y tilde bar, y dash bar, this new channel matrix h bar, h dash bar, this is a new noise n dash bar. So let's find the new aesthetics of these new parameters n bar, h bar and y bar. We know this n dash bar mean will be expectation of Rn inverse 1 by 2 n bar. Assuming n bar each element was 0 mean, then mean of n bar dash will be also 0. Covariance of n dash we can find now. Covariance of n dash equal to expectation of n dash into n dash Hermitian. This is nothing but Rn. So it can be written like Rn minus 1 by 2, Rn 1 by 2, Rn 1 by 2, Rn minus 1 by 2. This will be identical. So covariance matrix of new noise n dash is identical. That means elements are uncorrelated. Bar will be 0 mean and I as covariance. Now let's find statistics of channel vector h dash bar. H bar was complex Gaussian with zero mean and variance 1. So let's find this new H dash bar, which is Rn minus 1 by 2 H dash bar. Mean of H of dash bar equal to expectation of equal to 0, because mean of H bar is 0, so mean of Rn inverse 1 by 2 H bar will be also 0. Covariance of H dash bar equal to, similarly we can derive is Rn inverse 1 by 2 H bar into H bar Hermitian Rn inverse 1 by 2 H. This is a, I have mentioned this is a H bar is defined complex normal with zero mean and matrix as a identity. So we can write, so this will be Rn minus 1. So H dash bar is defined as complex normal with zero mean and variance Rn inverse. We have Y dash bar equal to H dash bar X plus N dash bar. Suppose W is the combiner at the receiver Rx side. So this. Now we can see that in the regular case, when y equal to hx plus n, where n are already uncorrelated and h was a given distribution, so there w was nothing but h vector divided by norm of h. In this case also, that is only difference is now instead of y we have y dash, h dash and n dash. So we can prove that the optimal combiner in this case will be, so this follows the same order what we did for the earlier normal MRC combiner, where noise was already uncorrelated. But here what we followed, make the noise uncorrelated by doing the whitening, then with this modified H dash find the optimal combiner W. So we can write this W as a so this is our optimal combiner for this system where noise are uncorrelated.